All right, here we're going to start talking about beams. And beams are slender members that have loads that act perpendicularly to their axis. And what we're going to look at here is shear and moment diagrams. And what this is it's basically a plot of the internal shear loading and bending moment along the beam's axis. And the whole point of doing this is to figure out where those maximum shear and maximum moments are occurring, because that's typically what we're designing for is the maximum. Okay, so the procedure to do this, if you've got a beam, I have just a standard beam shown right over here. The procedure to do this, first thing you need to do is calculate any reactions that you have. So I'd have to figure out what's going on at A and what's going on at C. Once I have those, generally we start it from the left, and we basically section the beam off into, anytime there's an abrupt change. So between A and B, between B and C, and between C and D. And we have a separate X coordinate. And basically what we do is we find what's going on within each section of the beam. Okay. So what we do is we draw a Freebody diagram, okay, of each section. So you make the cut, draw the Freebody diagram, and then you follow the sign convention for the internal loads, which is shown here, which oftentimes we start at the left and move right. So downward shear is a positive moment, and positive shear, and a counterclockwise moment is a positive moment. Again, that's on the right side of the beam. The exact opposite would be as if we draw the other side of the beam and we're looking on the left side here. But again, generally we work from left to right, so down and counterclockwise are positive shear and moment. Once I have those, I can go ahead and apply my equilibrium equations. That'd be the sum of the forces and the sum of the moments in order to calculate that internal shear and moment. And then you go ahead and plot it. And you've got, you're going to piece 3 different plots together to create one total plot. So then you can see how the shear and moment change as we move along the axis. So that's the general procedure that we do. There's also a graphical approach, and I prefer to use the graphical approach just kind of as a check to the procedure I showed previously. But just quickly, we're going to find some relationships here that are going to help us figure things out. So start here with the distributed load. So I have some random distributed load. I'm going to look at some little section here, delta x. Okay, so I've got a moment on each side, a shear on each side, and then again that distributed loading, which I can represent as a single force halfway across, which is delta x times that distributed loading, wx, over that thing. So I'm going to apply my equilibrium equations, sum the forces in the y, and I get basically v up, and then v plus delta v down, and then I have wx times delta x up. Okay, so your v's go away, and I can solve for delta v as wx times delta x. Okay, do the same thing with the moments. Again, I've got moment over here, negative moment, positive moment plus delta m, so that's a negative m plus delta m. I'm summing the moments about 0.0 here, so I have v times delta x, that's a negative moment, and then I've got the 1/2 delta x times wx delta x basically right there. Okay, my m's cancel here. Basically, I can solve for delta m is all of this. Now, what I do now is I basically take that delta x down to a dx, and what that does for the first one is I get dv dx equals wx. So the derivative of shear is the distributed load. And for the second one, this is a higher order term, dx squared. We can drop that off, and we're just left with dm dx is v. And this equation right here is the one that I use most often, is recognizing that the derivative of the moment is the shear, and I kind of just use that as a check from that previous moment. So that's really the main equation I want you to get here. Now, the other thing we need to look at is a concentrated force. Okay, so let's say I have a concentrated force on my moment. So I look just, on either side of it, okay, and I get a Freebody diagram that looks like this. So I've got v on one side, v plus delta v on the other side, and then f acting up. So the v's cancel out, and then delta v equals my concentrated load f. Now, if I've got a concentrated moment, again, I've got, I'm going to take the moments about 0.0, so I've got m, and then m plus delta m. Okay. and then I've got m naught. All right, so I've got all of those moments. Okay, and then I've got delta x times v. Okay, now taking delta x down to 0, that goes away, and I'm just left with the change in m, delta m equals m naught, that concentrated load. What does this exactly tell me? Well, it tells me that I get these jumps. So as my shear diagram goes across a concentrated load, it jumps by the same amount that my concentrated load is. Same thing with a moment. If I have a concentrated moment, my moment diagram will continue, and then it'll jump by that delta m, right? So delta m equals m naught, delta v equals f. So if I have these concentrated loadings, I get these jumps in either the shear or the moment, depending on if it's a concentrated shear, it's a concentrated force or moment. So again, I use these after I create my free body diagrams using the previous procedure. I basically use these as to, oh, yep, makes sense. That works. You know, I follow dm dx equals v. I get these jumps with f, and you'll see this when if you go look at the example, which I encourage you to do right now.